Okay, here we go. Let's do the systems of equation partial practice test. You'll notice on this first page that we've got 4 categories in the systems of equations, and the first one we're going to look at is identifying solutions. So you'll be expected to look at graphs and label them as no solution, one solution, or infinitely many solution. And we know when we see parallel lines, we know that they'll never touch, so that's going to be B, that is no solution. When we look at a line, this looks like just one line, but really what it is, it's 2 lines that are exactly the same line. So when you see this and you don't see another line somewhere, it's because both lines are right on top of each other. So they share all their points. That means that the solution, the points that the 2 lines share, are infinite, right? So it's infinitely many, or you could put infinite solutions. That's fine to put infinite solutions, or just put C. And then when you see number 3, you see 2 lines that intersect at one point. Once again, solution of a system is where they intersect, and in this case, they intersect in one place. So that would be A, one solution. You're also going to be expected to write an example of a system that either has no solution, like number 4, or one that has infinite solutions, like number 5. Once again, if we go back to number 1, we see that parallel lines are the kind of lines that have no solution, because parallel lines will never touch. And so when we think about writing a system equation that has no solutions, we're going to think of 2 lines that both have the same slope. So let's say my first line has a slope of 3, and it doesn't matter what the y-intercept is, it could be plus 10. Then the second line, if I want the 2 lines to be parallel, has to have the same slope, and it doesn't matter, I could put like 7,000. It doesn't matter what the y-intercept is, it's just that they have to have the same slope if you want a system that has no solution. For number 5, where we want a system that has infinite solutions, we're really looking to write 2 equations that are the same. Now you can't just go ahead and write y equals 2x minus 5 and y equals 2x minus 5. Yes, they're the same line, but they also look the same. So no, you cannot write that. What I teach in my class is I say write an equation of line in standard form, and we know standard form is where the x value comes first, and then the y value, then the equal sign, and then, the x term, then the y term, then the equal sign, then some number like 10. That's standard form, and that's a line. And then if you want to write another line that's the same line as that, but that looks differently, you pick a number to multiply it by. So I could pick like a 2 or a 3 or a 10, just something easy that's a number that's easy to multiply by. So I'm going to pick 2. So 2 times 2x is 4x, 2 times 3y is 6y, and 2 times 10 is 20. So when you see these 2 lines, they look different. The line in the blue looks different than the equation in the green, but we know they're exactly the same. If we took this second equation and divided each term by 2, we would be back to the first equation. So this would be an answer for this type of question. There's infinite amount of answers for both 4 and 5, and everybody's answer is going to look different. Okay, let's look at 6. It says, is 2, 4 a solution to this system? Basically what they're saying is that they solved this system right here, and they want to see if their answer is correct. They think that 2, 4 is the point where both of these equations, if we graph them, that 2, 4 is the point where these 2 lines would intersect. And so how we're going to check them is this. We're going to say, okay, if that's true, then when I plug 2 in for x, I'm going to plug 2 in for x, and I plug 4 in for y, plugging 4 in for y, that when I put that in my calculator, it should equal -2. I'm going to do this in my head real quickly. So we'll have 10 minus 12, which yeps, yep, that equal, yep and yes, yeps. that equals negative 2. So it works for this one. And you're saying, oh, great, then yes, it's a solution. Not so fast. It has to work for both of them. So now we're going to do the same thing. We're going to take the 2, and we're going to plug it in for x for this equation. So we'll have negative 6 minus 3, plug in 2 for x. And we're going to take y and plug it in. I'm sorry, we're going to take 4 and plug it in for y. And then we're going to simplify both sides. If I put this side in my calculator, I'm going to get what? Negative 6 minus 6, that's negative 12. If I put this side in my calculator, negative 5 times 4 is negative 20. Those are not the same. So if if it didn't work out for the second equation, then this is not an answer for the system. It's no. You're going to have to write no. So you'll show that although it worked for the first one, it didn't work for the second one. It has to work, the answer has to work for both equations for it to be considered a solution to the system. Okay, now we're going to move on to finding solutions graphically, the next section of your test. Now, I didn't have all of the different types of identifying solutions for the previous problems because this is a partial test, but it gives you an idea of what you need to be prepared for. So finding solutions graphically, we're going to look at problems like this where our equations are in slope-intercept form, and we know that when we graph, when they're in y equals mx plus b form, we start with the y-intercept and we put a point there, that's negative 7, and then our slope is 2, which we consider 2 over 1, so it's up 2 over 1. I always like to do a couple of points, get a couple points in, so it makes it easier to see where my lines intersect. All right, so I'm going to connect these points, and then I'll graph the second line, which my y-intercept is negative 2, and my slope is negative 3, which is down 3 over 1. Look at that. Right away, I see where they intersect. It intersects right here at this point. And then you're going to have a line on the test that asks you to put the solution. Remember, we put the solution in a coordinate point form where we have the parentheses. We put our x value first. So to get to this point, we go over 1 on the x axis, and then we go down 1, 2, 3, 4, 5. Kind of looks like we're not really totally over there, but we are. So down 5, so it's negative 5. This is your answer at this point. Okay, checking out our time. Okay. So the next question, same thing. The first one's in slope-intercept form. So let's go ahead and graph this. My y-intercept is negative 3. My slope is 1/2, so that's up 1 over 2, up 1 over 2. We'll do it a few times. I'll even go backwards and put points in here. So I'm ready for any intersection that may happen. All right, and then the other one I'm going to have to do a little bit of work on before I can graph it. Actually, I'm not going to do it to the side. I'm going to do it right under. I'm going to distribute my 3. So I'll have 3x plus 6 minus 14, and then I combine my like terms. So I have y equals 3x minus 8. So negative 8 is my y-intercept. And then my slope is 3, so that's up 3, 1, 2, 3 over 1, 1, 2, 3 over 1, and there we have it. We've got our intersection right here, and once again, the solution to a system is where the two lines intersect. So the answer has to be written in point form, coordinate point form. So to get to that point, we go over 2, and we go down 2. So remember, points are the exact opposite of slope. Slope, we do y over x, right? Change in y over change in x, rise over run. But a point is different, and you can tell that naming a point is different because we use parentheses. But we don't use parentheses in slope. We do slope. Okay, and so here we're going to do what we call the cover-up method, which basically, pick this up, excuse me. So the cover-up method basically says if we cover this up and we just looked at what's left, we would have 6y equals negative 12. We would divide by 6, and we'd see that y is equal to negative 2. Since it says y equals -2, we'd go to the y-axis and we'd put a dot on -2. That's one of the dots for the line. Then I'm going to erase that because let's cover up the other way. If we covered up 6y, what we'd have left is -6x equals -12. And we're going to solve for x by dividing both sides by -6, and we'll get x equals 2, which means go to the x-axis and put a dot on the 2. And the reason why we cover up, when I'm covering up the y, I'm saying, hey, if y is equal to 0, then this whole thing goes away. That's why we call it the cover-up method. It's actually called the intercept method because we're graphing a line based on its x and y intercepts. All right, and so then when we do the other, let's erase this. When we do the other equation and we make x equals 0, that means this whole term is gone, and this is what we have left. So we're going to do -2y equals 10. We'll divide both sides by -2, and we'll get that y equals -5. That means go to the y-axis, find -5, and put a dot on it. That's its y-intercept. When we have a y-intercept, that means that our x is equal to 0, which is why we covered it up. Now we want to find the x-intercept, and we do that by covering up the y, setting y equal to 0 so it goes away. And what we have left once we cover that up is 2x equals 10, and we solve for x by dividing both sides by 2. So x equals 5 means go to the x-axis, find the 5, and put a dot on it, because that's that equation's x-intercept. And let's connect the dots, and can we see what's going on here? We've got two parallel lines. Are these parallel lines ever going to intersect? Sorry, intersect. They're both a little similar there. Are they ever going to intersect? No. That's why there will be no solution, because they're never going to intersect. Okay, and so our next little partial practice is going to be on the section for finding solutions algebraically. So in this first one, we're going to use substitution to solve. So it's y equals 5x plus 8 and y equals -3x minus 8, then we're allowed to set them both equal to each other. And once we do that, we're going to solve for x. We're going to go ahead and, can you come back and just give me 5 minutes? Thanks. All right, so we're going to go ahead and solve for x. So we're going to add 3x to both sides. So we'll get 8x plus 8 equals -8. Then we'll subtract 8 from both sides, and we'll get 8x equals -16. We're almost done. We're going to divide both sides by 8, so we'll get that x equals -2. And it feels like we're done because we solved it. So we've got x equals -2. But remember, a system, when we solve, the answer is going to be an xy coordinate point. So that means we've got to take this answer, and we've got to plug it in. I'm going to pick the first equation, but we could have used the second equation as well. I'm going to plug it in when I see x, because now I know x is equal to -2. And I want to find out, hey, what's the value of y when x equals -2? So I'll go ahead. 5 times -2 is -10. I could have just put this in my calculator, right? And I got y equals -2. So the answer to this system of equations is -2, -2. This next one, it's set up, although we use substitution for number 8, for number 9, it's set up so that we can use elimination to solve. And the first thing that we're going to do with elimination is ask ourselves, are they both in standard form? And so we look at this second equation and we're like, sure, this is in standard form. The x term, then the y term, then the equal, then the number. That's good. But this one, not so much. We're going to look at 4y equals 11 plus 3x, and we need to get it in standard form. So I know I need to get this 3x over to the other side. Anytime I want to move something from one side of the equal sign to the other, I've got to do the opposite. Since it's plus 3x, I'm going to subtract 3x from both sides. I'm also going to get rid of that line because I'd hate for you guys to think I'm dividing. All right, so I'm going to subtract 3x from both sides, and that goes away, so I have an 11 here. 4y minus 3x, they're not like terms, we can't combine them, so I'm going to write it like this, negative 3x plus 4y, and I'm doing it that way. I could have written 4y minus 3x, but in standard form, our x term goes first. So I just rewrote this equation to look like this because we have to have it in standard form to do elimination. So now I'm looking at my two equations. That's one equation, and this equation over here is another. And I think, okay, if I put them right underneath each other, would anything cancel out? No, nothing's going to be eliminated. And so I think to myself, well, I could simplify. I look at this equation and I think, is there a number that goes into 6x, negative 8y, negative 18? Why, yes. 2 does. So I'm going to divide every single term by 2. And when I do that, I get 6x divided by 2 is 3x. Negative 8y divided by 2 is negative 4y. And negative 18 divided by negative 2, divided by 2 is negative 9. When I do that, it's awesome because now this equation and this equation will work when we use elimination. So what we're going to do is we're going to take both equations. We'll take that one, and we'll take this one, and we'll write them right underneath each other, and we'll add them together, and we'll see that negative 3x plus 3x, gone, eliminated. Oh my goodness, it's our lucky day. 4y plus negative 4y, also gone. When everything's gone, when all the cookies are off the plate, what's left? The number that stands for everything's gone is 0. Nothing's left. And then we have 11 plus negative 9, which is 2. When x and y are out of the picture, or when they're both out of the picture, and we just have numbers left, we have to ask ourselves, is this a true statement? Does 0 equal 2? And we have to answer, no, it doesn't. So that means there's no solution, which that means if we graph this, we would have ended up with 2 parallel lines. Okay, this next one is nicely set up because I see the 3x. I see the 3x. And if I subtract these two equations, then the x's are going to eliminate. So I'm going to say 3x minus 3x, gone. Negative y minus a 2y is going to be negative 3y. Note, when you subtract one equation from the other, you keep having to bounce off of that negative sign. It goes for all 3 terms. And so then I put the equal sign, and 11 minus the 23 is going to be what? Negative, I'm blanking out here, negative 12. Does that sound good? Yep. And then to solve for y, I'm going to divide both sides by negative 3. I know some of my students freaked out a bit when we solved for y first because they're so used to solving for x first. But it's okay. We're going to use y equals 4, and we're going to plug it in. This time I'm going to use the second equation just so I can avoid that negative y. And I'm going to rewrite the second equation, but when I see y, I'm going to plug in 4. So we're allowed to plug in y and solve for x. That's perfectly fine. And I'm going to simplify this a little bit. 2 times 4 is 8. And I'm going to subtract 8 from both sides. So I get 3x is what? 15. And then I'm going to divide both sides by 3. So x is 5. And don't forget that the system of equations, its solution has to be written as a coordinate point. This is the point. If we graph those 2 lines, where they would intersect at 5, 4. This next one, when I look at it, I can't go straight to adding or subtracting because 30 and 18 are not going to cancel out, and 10 and negative 6 not going to cancel out. So what I'm going to do first is I'm going to do a little simplifying. I'm going to go ahead and look at this first one and say 30, 10, and negative 15. What goes into all of them? 5. So I'm going to divide every term by 5. Let's see, I'll write it this way. So 30x divided by 5 is 6x. 10y divided by 5 is 2y. Negative 15 divided by 5 is negative 3. And then I'm going to do the same thing over here. I'm going to see that, probably need to do it in a different color. I see that 3 goes into all 3 of those terms. So I'm going to divide every term by 3. Negative 18x divided by 3 is negative 6x. Negative 6y divided by 3 is negative 2y, and 9 divided by 3 is 3. Well, this looks like it's going to be a lot of fun to do, because watch what happens when we add. That gets eliminated, that gets eliminated, that gets eliminated. Now, let's stop. When everything gets eliminated on the left side, we have nothing left, which is 0. When everything gets eliminated on the right side, we have nothing left, which is 0. Does 0 equal 0? Yes, it does. And so when we can answer yes, we know that our answer is infinite solutions. That means if we graph these two equations, their lines would actually be the same exact line. Their points, they would share every single one of their points. There would be an infinite amount of points that they would share. That's why their solution to this equation, this system of equation, is infinite solutions. Okay, now we're moving on to solving systems in context. And so workers at Lexi's mowing company can mow at a rate of 300 square feet per hour, while workers at Max's mowing company can mow at a rate of 700 square feet per hour. If each worker at Lexi's gets paid $12 an hour, and workers at Max get paid $25 an hour, how many workers were used from each company if 6,400 square feet of lawns were mowed in an hour, and the cost was $235? Whew! Okay, we have two things going on here. We've got square footage, so we've got 300 square feet, 700 square feet, and 6,400 square feet. We know that 6,400 square feet is going to be our total. We know that Lexi's, and a lot of you don't like it when I'm using the L and the M. I'm just doing that to make it more applicable to the word problem. So at 300, workers at Lexi's can mow at a rate of 300 square feet per hour. So I'm going to put L because the 300 goes with Lexi's workers. And then the workers at Max's company can mow at a rate of 700 square feet. So I'm going to put that there. So that is one of our equations. It is the square foot equation. Then we're going to look at the dollar amount. And so Lexi's workers get paid $12 an hour. So that's going to go with the Lexi workers. And Max's workers get paid at $25 an hour, which seems like the better place to work if you ask me. And then altogether, our last, excuse all the announcements, our last dollar amount is the $235. So we're going to set that equal to $235. So once again, we're going to have two different equations that stand for two different things. In this case, we've got the rate of work equation, and in the next place we've got the money equation. Okay, so when we look at this, we want to go ahead and solve it, even though it says do not solve. Why not? Let's just go ahead and solve it. So actually, I'm going to stop right now, and I think, yeah, let's go ahead and solve it. It's going to make this tutorial a little bit longer, but I think we can solve it. Hold on, and let me see if I can pause 1 second because the student is here, and I'm hoping I can pause.